Free spectral range is a figure of merit for a Fabry-Perot interferometer, and I'll just cover briefly here. We talked about the Fabry-Perot interferometer already in class. Remember, it's made out of two parallel mirrors with their shiny sides facing each other, and they're semi-silvered, so light can come in and penetrate through the mirror partially. It's confined within the space here. If we send an array down here, ray n, and we send in another ray above it, ray n plus 1, ray n will proceed through the cavity. It will bounce from the opposite mirror and come back and combine with ray n plus 1, and then they're overlapping each other and they might be out of phase, giving you a destructive interference out here where it emerges. So we need to look at the condition for destructive interference, so that's what we're doing here. And there's a phase difference between these rays when they overlap, and we talked about that in class as well, where phase difference is 2 pi times the fraction of a wavelength that is equal to the difference in optical path lengths. We worked that out in class as 2 mirror separation d cosine theta, with theta is angle of incidence, over lambda, and you can replace lambda with c over frequency, and so I might do that right here so I can have the expression for the phase difference in two different forms. And what I point out is that phase difference depends on a variety of things. It depends on the separation of the mirrors, it depends on the wavelength of the light, and the angle of incidence of the light. Consider the effect of each of those separately on that phase difference and look at how each one of those properties affects then whether you have constructive or destructive interference. No matter what, if you have constructive interference out here, the phase difference has to be an integer multiple of 2 pi. So I'll write that down as the condition for an interference maximum, which I'm going to rename a fringe, because that's what it looks like when you actually see it on a screen. We'll see those in the lab experiment. So these two conditions have to be met, where 4 pi times the mirror separation times the frequency over speed of light has to equal 2n pi. We're typically going to let cosine of theta be 1. That is, in most practical situations, you have normal incidence. So now we can define the free spectral range, which is the frequency difference between adjacent orders of interference. So if I have a bright spot here or a dark spot here or a bright spot here, the frequency difference that induces that is the free spectral range. And n is just an order of interference, and it's going to become unnecessary to even think about very quickly here. A way to see the free spectral range is imagine what you have on the left side of this mirror assembly is a monochromatic light source with variable wavelength, and you have a knob on that light source, and you can adjust the wavelength of light coming out. So I sweep through wavelengths or frequencies. I sit out here on the other side, the right side, with a, say, a photodiode, detecting whether I have bright light coming out right here or dim light coming out right here. And as I sweep through the frequencies here, or the wavelengths, as I go through an amount of wavelength difference that's consistent with this definition of delta equals 2 pi times an integer, I will see the light right here at this point cycle through bright, then dim, then bright, then dim, then bright, then dim as that frequency changes. And how will that be? Well, if I look at that frequency difference between two adjacent interference maxima, I'll say delta for n minus plus 1 minus delta for n, delta for just two different neighboring bright spots and dim spots as I cycle through the wavelengths out here. That has to be 2 pi. We have the phase difference as 4 pi d over c times frequency times cosine theta, which is 1. That 2 pi has to equal 4 pi d over c times the difference in frequencies, or put it in terms of the difference in frequencies, rearrange it. So the difference in frequencies is, cancel your 2 pi's, it's c over 2d. That's the free spectral range. And the difference in frequencies, sometimes people refer to 2 pi as free spectral range. I find that rather uninformative, but I find this to be very system dependent and informative. You could also write it in terms of lambda, right? Since nu frequency is c over lambda, just make that replacement and cancel the c's. So you could say the difference in 1 over lambdas has to be 1 over twice the mirror separation. As you cycle through wavelengths, you have your source over here, you're turning that knob on the source, making the wavelength go up and up and up and up. As you cycle through wavelengths, when the difference in 1 over wavelength to just different wavelengths is 2d, you have the exact same brightness out here. So if you get a really bright spot and keep changing the wavelength, when the wavelength is changed by 2d, you'll have another bright spot.